and Martyn from Lestercast, who's going to give us a fantastic presentation this evening about the Bentley Motors Flying Bee. Russell.
Thank you, Trevor, and thank you to everybody here this evening online. It's good to see such a good attendance. I think it's about a year ago, Trevor, that we met, or just under a year ago, that I got accosted in Dusseldorf by Trevor asking if we would do a presentation for the ICME. Of course, we said yes. We was in Germany. Everything seemed like it's a sunny day, I think, as well. And it seemed like a good idea at the time, and it's still a good idea tonight. So we wanted to promote, or present rather, the Bentley Bee, the sort of iconic casting that we make at Lestercast. I myself have been at Lestercast for 3 years this year. Prior to that, worked with Simon and David at Microsoft. Some of you might have known me from there. And prior to that, working at various foundries in the UK over the last 25 years, I might add. George Fisher is where I started as an apprentice pattern maker, and then moved on to Weir Minerals in Todmorden, Russell Ductile Castings in Scunthorpe, and so on and so on. So I've only really been with Lestercast for 3 years. Martyn, he's going to introduce himself in a moment, has been involved with the Bentley Bee since its inception. So when we were asked to do this presentation, I thought it was only fair that Martyn really should be standing up and doing quite a bit of the early groundwork and explaining what happened in the early days of the inquiry. So you got a bit of a bonus presenter tonight. So I'll hand you over to Simon, to Martyn.
Yeah, again, as Russell said, thanks for giving us the opportunity to talk you through really the story of the Flying Bee. I joined Lestercast in 2015 and as technical manager at the time, and yeah, sort of lived through this. I didn't have a grey hair before we started this project, so it's been quite intense and took quite a number of years to get to where we are today. So I'll start with an overview really about Lestercast. Not here to promote Lestercast, but just anybody that's not heard of us. We're a leading UK investment casting manufacturer, and we're based in Leicester. We just can't spell Lestercast, that's all, that's the problem. Established over 50 years ago, we were founded in 72. So we celebrated 50 years in 22. And our current owners took over the business in 2001, having both worked with investment casting companies previously and got the opportunity to buy Lestercast, and they transformed the business from what it was at the time to what it is today. We're employing currently 40 people. I think we've been up to sort of 43, 44, but we're currently 40 people, so relatively small compared to some of the other businesses that's in the room tonight. We manufacture bespoke and quite often extraordinary complex castings. We get customers come through the door with a broken part in his hand, and can we reproduce it in some way? So we have various ways and means of reverse engineering and producing wax patterns, 3D printed, and allows us to produce replacement complex parts. But as well as that, we're supplying many big OEMs around the world with not only one-off prototypes, but high volume production as well. And we manage that by working with partners overseas who produce the larger volume work for us, and it's managed through Lestercast and comes in through Lestercast, as well as the larger products that's way too big for us to cast within our facilities. So we can produce and supply large product, high volume through our outsourcing option. We're ITF. I don't think there's many other investment casting foundries in the UK that are ITF. Of course, it was a Bentley requirement at the time, hence going for the ITF and ISO 9001. And we're also fit for nuclear. Got no work, but we're fit for it. For those of you that's not familiar with the loss wax process, very simple explanation. We start with a wax pattern, and wax patterns can be produced either through 3D printing techniques these days, or by injecting wax into a die. Once we have the patterns, we then assemble those onto a tree, as we know it, a running system, a tree, getting multiple parts on there, off a sprue with an integral pouring cup. Once we have the wax assembly, we then start to invest it or coat it with ceramic, and that's where the investment name within the investment process comes from. We're investing the wax with ceramic, typically 7mm thickness layer, built up of various grades. And I think further in the presentation, there's some more information on the grade makeup for the coatings that was used for the Bentley. Once we have a ceramic mold, we then have to de-wax. So we remove the wax from within the tree, and that's done in a boilerclave or an autoclave steam pressure vessel that melts away the wax. So when we start looking at assembly techniques and putting patterns on a tree, we also have to think about evacuating wax as well. It's not just a case of just putting it in any orientation. There's thought given to how we actually assemble those patterns, not only to aid feed techniques and running techniques, but also to aid evacuation of the wax. And then, as with other casting process, we then cast material into the ceramic, allow it to solidify and cool, and then we knock it out. So we vibrate the ceramic from the casting. We can then cut the parts off using high-speed friction saw, and then parts are then available for finishing. So we've brought a few examples of castings for the Bentley B tonight. So after the presentation, by all means, come and have a look at sort of surface finish and detail and integrity that the process allows us to deliver. We cast mainly steels. I think that's fair to say. Probably 98% of what we do is steels of various grades, but we do cast aluminium, brasses and bronzes. We don't do iron. That's the only thing we don't do. Okay, so the story of Bentley and Lestercast originated before my time in 2008, when Lestercast was given the opportunity to supply the first Flying B, and it was seen on the Mulsanne, which was the coach built, I think they called it, Mulliner. So it was optional extras onto the Mulsanne, which gave you the B and a stainless steel polished wing vent that sits there just at the back of the wheel. So the Flying B for the Mulsanne, again 316 stainless, hand polished, and we did about 25 a week if business was good. So in the scheme of things, sort of low production. Then along came the wing vent in 2011 as an additional optional extra, and that ran for 5 years. Again, 16 a week, so not big volume. Then in 2019, we started production with the current illuminated Flying B, which is this one here. And that's an optional extra on the flying spur. So it doesn't come with the standard price tag. You have to pay extra to have the B on the bonnet. Again, it's a 316 stainless steel, and a lot of the quality requirements were a carryover from what we're doing on Mulsanne. So the challenges for us as a casting, we'll go into detail in a moment. There's also, as well as the polished, if this works, there is also a what they call a black pack option, where you can see that. So instead of the mirror polished stainless, this is a black anodized finish. For some vehicles, they go full black pack. So all the chrome work is converted to this black finish. Not quite my cup of tea. I think if you're going for bright wear, you want the polished mirror finish. But they do sell it's about, I don't know, 95% is polished and a small percentage is the black pack. Open 3 times. Okay, so timeline. It was always Bentley's intention to launch the new Flying Spur in 2019, which was Bentley's centenary year. Didn't quite work out that way, but that's another story. So in June 2016 to May 18, we were involved with product and prototype development. And through that phase, and I'll show some images of all the different derivatives we got to before this came along. There were 11 different derivatives produced of various shapes and sizes for various applications. In September 16, we received the original bid specification for the part, which, as you'll see from this document, bears no resemblance at all to actually what we have on the table today. They'd got this vision of slices of material to sort of form a 3D geometry, which looked bloody awful. However, we were asked to quote on that basis, which we duly did, and the rate at the time was 39 a week. Again, 316 stainless. Then in November 17, we were actually nominated for series production. Having gone through some prototype development work, they then nominated for series production. And in July 18, we ordered production tooling. October 18 was initial first off samples, and May 19, production commenced at a rate of 100 emblems per week, which, as you can see from those figures, is significantly higher than where the Mulsanne has ever been. We did actually peak 120 a week in December 20, which was quite a challenge because everybody was coming out of COVID. We've got skeleton crews running, and Bentley were putting pressure on to say we want to get this build this stock up ready for launch at the end of 19. And we were achieving these sorts of numbers with limited staff, and it was quite a challenge, but we got there. Unfortunately, it was January 2020 when they launched the new flying spur, so they just missed the centenary year by a couple of months. No fault of Lestercast, I might add. They had problems with the rad shell, which is the section at the front of the vehicle where the emblem sits, but it was a sizing issue, I believe. The emblem traditionally is comprised of a mascot, which is the B shape, and the plinth, which is the foot that sits on the surface of the bonnet or within the bonnet, as it is on this new one. The original one was, although it was mechanically operated, it was a lever and cable system from within the driver's seat to actually raise the emblem out of the bonnet. Things evolved somewhat with the new one, and I'm just going to click on this video, which will show the mechanism that sits within the front of the bonnet, what we've got here today. So, Russell, if you'd like to do your business, we did manage to acquire one of these from Bentley for our reception area. So, as you see, when the vehicle is parked and the vehicle is locked, there is a flat badge that sits on the bonnet. Unfortunately, the flat badge is plastic chrome plated. The reason for that, and the reason that they didn't go a polished stainless steel, was weight related on the mechanism. So we have, you've got a £350,000 car with a plastic chrome plated flat badge, but we don't mind. We've got the Flying Bee illuminated there that comes out the bonnet, and there's a knockdown feature as well. So if it's involved in a front end impact, the emblem disappears into the bonnet very quickly. Yeah, probably drag your hand in if you were polishing it. So that's how the mechanism works. That was designed by a lead engineer at Bentley. They did outsource the mechanism concept, but in the end they decided to design in-house, and that was the outcome of it. So that is a bit of an internal view of what's happening in there. On the previous emblem, the condition has always been a mirror polished, corrosion tested. No different with this one. So our criteria was 316 stainless steel, heat treated using a HIP process, CNC machined, They wanted full traceability of every casting down to melt, material lot. So we had to come up with some means of putting traceability on both the plinth and the emblem. And the real challenge when we got into the technical stuff was they wanted an internal wire routing channel that you see from this section here. It's 3 millimeters by 6 millimeters, which takes 2 1 millimeter wires from the illumination on the inside down through into the battery area. So as a casting goes, that was the challenge. We knew we could produce polished emblems, but could we actually produce one with an internal wire routing channel? And of course, Bentley, they put SCs on the drawing for control of significant characteristics. So we've got a number of gauges in place for series production to control those particular features. Yeah, the concept of the Flying Bee was very much design driven, not designed for manufacture. So again, when we started to look at simulation, which Russell will get in some detail shortly, basically they designed something that we couldn't feed and we couldn't get total integrity. So there was a few challenges there. The concept for the emblem was put out to the engineers within Bentley, and I believe there was 50 applicants that had designed this Flying Bee, all got their own ideas. And in the end, it was a Korean engineer called Ho Young Hwang, who was the competition winner. I don't know what he won. I don't think he won a car or an emblem, but he was the winner. And his concept was of a swooping owl coming down and morphing into this emblem on the front of the vehicle. So what floats your boat, I guess. Unit weight, it's only 165 grams, and dimensions are relatively small, 49 by 81 by 68 millimeters. So casting challenges, thick and thin wall sections, we try to set a nominal no less than 1.8 millimeters, but we had some heavier sections, few still in existence, up to sort of 7.5 millimeters. Isolated sections within, complex geometry, tight corner and fillet radii down as 0.25 of a millimeter to half millimeter radius. Yeah, it doesn't help us within our casting process. And of course, an internal smooth cavity. It was okay producing a cavity to pass wires through, but we needed to ensure that those wires could be passed smoothly by the assembly team. So that was also a challenge. And typical casting tolerances plus or minus 0.3 of a millimeter on cast features, and a little bit tighter on machining. Here, hopefully, we can load the CAD assembly. So you can see the components we have within this. At the bottom is a pivot adapter. I'll just hide the plinth. So the pivot adapter mounts on top of the mechanism and is allowed for this knockdown feature. So there's some spheroidal profiles here that allows the knockdown feature to work. Here we've got the lenses inside the wings, and inside there you see the PCB board, which is the LED part that sits within. And again, on the table here, we've got an example of one with one lens in and one lens out, so you can actually see the inside profile of that. So we have the full CAD assembly. Okay. I talked earlier about the prototype development, and this is a bit of a timeline and the derivatives that were being tabled at the time. This started in June 16 through to May 18, and our codings for part numbers, quite simple. If it's Bentley, it starts with a B. 34 was our 34th customer that started B, and we started with RP1, which is rapid prototype 1, 2, 3. The current production part number is B3437, and we're now at K. So there's been quite a few changes since we actually started production. These images here are just a few examples of the different derivatives. Initially, they were looking at integral feather design, again, a bit like the original Mulsanne. And then they were looking at another option. I'll just click, I am conscious of time. They had some concept of the wings themselves being cast separately, so that the customer had choice when he ordered his vehicle to have the wings painted in a different color or even to match the vehicle. That idea didn't last very long. I'm not going to click through all of those, but if anybody wants to have a look at some of the other derivatives, they're contained in there. There was also, once we were getting nearer to series production, there were some requirements for a disguised emblem, because they were starting to do road test with this emblem on the bonnet. So they asked us to produce a casting that was disguised from how it was going to look in when it was launched. So this was disguised. It still had some illumination in it, but it bears, again, no resemblance to the current emblem. Okay. Prototype development of the illuminator design started in October 17 with the initial concept of, can we actually produce this part? We didn't know. So we needed to go the 3D printed prototype route. We'd already worked with a company in America called Eagle Engineering Solutions, who had done some 3D printed ceramic work for us. So I approached Eagle and said, look, we've got this project. It's going to need some fairly detailed 3D printed ceramics for the internal core, and of course some 3D printed wax patterns. And they supplied a number of 3D printed ceramic and wax patterns. The few images on here. So they were the 3D printed cores, and the patterns were printed in two halves and the ceramic laid inside and then sealed. So we've got a full sealed resin pattern. Of course, we needed to do some X-ray on those patterns to make sure at this stage we had no breakage. We didn't know what was going to happen with that core once we started putting stainless steel in the mold, whether it was actually going to break and fracture. So we wanted to ensure at that stage that we knew we'd actually got a sound core within the wax. So we did some X-ray images. These are a few of the initial prototype parts, which were reasonably successful. We did have some, you can see here, we did have some misrun on the wings, and we established that we were actually under the 1.8 millimeter on metal section locally in some of these areas. So a little bit further on in the presentation, you'll see some of the design changes that were required to assist. We then moved on with further illumination parts, and we started then to get into specific vehicle builds and all these, as you can see, rapid prototype 30. So we did 30 rapid prototypes before we even started looking at production. And that was 27 off, and for all of those steps, we used Eagle in America to supply complete patterns that we could just assemble then to a technique that we'd established, and it allowed us to supply the initial requirements before tooling was required. At that point, I'll hand over to Russell.
Thanks, Martyn. Cheers. Just standing in front of the camera. Yeah, so as I've already mentioned, I joined Lestercast just over 3 years ago, or I got involved in this project over 3 years ago. There was some issues with the production parts, mainly porosity, which was coming out and causing some problems with parts out in the field. And Martyn and the team asked me to get involved at that time from a Magmasoft point of view, looking at some of these issues, and you can see here the Magmasoft results versus the real world results as porosity in that small section there. I think Martyn's already mentioned it on the previous slide, or one of the first slides. It was not designed for manufacture at all, so it was quite a challenging casting. Obviously, it's a small, intricate casting, but the same principles remain. There was isolated sections around here that we couldn't feed or get feed metal to. So there was quite a lot of to and froing between Lestercast and Bentley at the time, looking at what could be changed from a design point of view, what could be saved. Obviously, these parts are already in production, so it was very difficult to do a complete design change. However, obviously, with the use of Magmasoft, we were able to establish what the issues were. This is a view of the solidification. You can see here there's two isolated sections down in the corners here around the core, which was manifesting itself as porosity, or shrinkage rather, in the casting. So quite a lot of to-ing and fro-in and design changes later. Managed to change the profile, which was this internal shape here. So we did have a little bit of scope to change that. Obviously, it was an internal shape, so Bentley themselves weren't too worried about that. They're a bit more flexible. And we're able to increase the corner radii here from 0.5 millimeter to 1 millimeter, which sounds absolutely nothing, but we're talking about small margins here. And again, through use of simulation, we're able to prove that some of these small changes, albeit fairly minor, it gave us a much better result, which is the one you can see here. Oops. There's no isolated sections there. I'll try and play that again. So we get a good solidification back to the feed gate, which is on the top there. You can't see that on this simulation result, but I think we moved the feed gate back as well at the time, just to try and get the main section fed with liquid metal for as long as possible. And that eliminated the shrinkage, and obviously we're able to see that in reality. Bentley were very pleased. I think Lestercast were very pleased as well. It was an issue that was had been around for a long time, causing them some problems out in the field. So that was resolved. Again, you can see it before and after here. On the face of it, it doesn't look like a massive change, but yeah, we're talking very specific solidification around this area, and obviously we needed to change that. So that was successful, and that worked and resolved one of the major problems, really. So it's lucky that I got involved in this about 3 years ago, wouldn't it? So it's certainly reduced the scrap rate, that's for sure. Some of you might have seen this before. This is a Magmasoft filling simulation of part of the investment casting process. So what we've got here, I'll play that again. We've got a reservoir of metal, which basically is at the bottom of here. This is effectively our crucible, our furnace. We place the shell on top of the furnace, we roll it over. So what you can see in this movie here is it's going to play for me. There we go. We can see the metal cascading down into the tree, and then obviously into the individual parts down here. And we're looking at a temperature scale here. So this looks from the pouring temperature, which is set at 15 C, down to the liquidus of this particular 316 alloy at 1428. So we knew that from a filling point of view, we were getting nice hot metal into these areas. There's quite a lot of work done back at the early stage of the project as well, and continues to improve to try and reduce the turbulence in this, I suppose, filling sequence, introducing filters and so on to help improve the repeatability as well as the quality. So going back to the production side of things, Martyn's mentioned the core. So not only was there a wax tool, a soluble wax tool, but there's also a core tool as well. Production tooling was ordered in July 2018. and the first of 10 samples produced in 12 working weeks. Arthur Jackson and Co in Brighouse produced the tooling, which is the ceramic core tool, the soluble wax die, the pattern die, and also the core assembly jigs, which we'll show you a little bit later. And the ceramic cores were, and continue to be at this moment, produced by Morgan Ceramics, or Certec of Corby. This is a view of the ceramic core tool. It's a 2-impression core tool. It's water cooled as well to try and keep the temperature as even as possible, let's say, from one shot to the next. And yeah, we produce the cores in that fashion. I think there was a couple of different options of core types and materials at the time, but using, I think, Certec or Morgan's expertise, we're able to determine what type of ceramic should be used. Obviously, there was some trials going on, I think, partly some of the trials that were done through Eagle, looking at obviously how to remove the core afterwards, which is something we're going to get to in a second on a later slide. But yes, it's a semi-automatic tool. It's got manual ejection, manufactured from a P20 steel, 72-hour core firing time, and obviously being a key feature, needs 100% gauging as well. So there's some features on here that get gauged once the core's been fired. Those gauges are currently at Morgan's, and we also have a secondary gauge at Lestercast. So we're checking the cores as they're coming in. I mentioned the soluble wax die. So the die itself, again, was manufactured and designed and manufactured by Arthur Jackson's. The soluble cores are actually manufactured by another supplier into Lestercast, Blason. I don't know if anybody knows of Blason, but they produce all of our soluble waxes. And we went down the soluble core route because of the complexity, effectively, of the wing area. It wasn't easy to remove that from the or produce a tool that would make that in a conventional way. So for quite a few years, Lestercast have used this technique, which is a soluble core material, and we've got some soluble cores as an example on the table. And effectively, we get those manufactured. It looks like a normal wax, effectively. And once we've manufactured that, we put it into the wax injection die, and then we inject our casting wax around it. To then remove it, we dissolve it in citric acid, which basically attacks the orange soluble core, but doesn't attack the green wax. So effectively, then we're left with a very complex shape that ordinarily wouldn't be able to be made by conventional tooling means. Leaching time is around about 12 hours. It depends how much volume there is in the soluble core itself. This is a technique that we use at Lestercast for, again, lots of complex shapes, pipes and exhaust ports, something that would be very difficult to make from an aluminium die and a wax in that fashion. So it's a good technique to have. And then the pattern wax die, which you can see down here, it's a single impression. It fits onto one of our semi-automatic machines. It's got separate loose piece as well. The loose piece, which you can see here, comes out with the wax. It gets ejected. The operator takes the wax out of the tool, removes the insert separately, and then puts the inserts back and starts the process again. So cycle time, 90 seconds per core. There is some pre-assembly that's involved as well. So I mentioned the soluble core is put into the wax die. There's also the ceramic core as well. I'm not going to pick that up because I'll break it now, but I'll let you guys break it when it goes round. But yeah, so it's in terms of the tooling complexity, it wasn't just the shape. It had to fit a soluble core, which obviously has its own contraction. It has to fit the ceramic core as well as an assembly, and then it all has to be surrounded by liquid wax. So you've got all this expansion of 3 or 4 different materials going on, and what you're hoping for is the ceramic core doesn't break during that pressure of the wax going in. This is before we've made a casting, by the way. actually making the waxing itself. So there was quite a bit of work that was done, I think, to be fair, in the early stages to get that tool working, again with contraction rates and clearances, etc. So we're now on to tool number 2, I think. So we always had a second die made at the start just in case. Going back to the ceramic core, which you can see in the top left here, I mentioned about the gauges that we use at the core manufacturer. We also have gauges back at base to check the cores. And then this is a multi-cavity assembly fixture, which allows us, or the operators, let's say, to preload the soluble cores and the ceramic cores together. So they can preload them, they can check that they fit, they glue them into one another, and then they put that whole assembly into the wax die, which you can see, sorry, just down here. So you've got your soluble, you've got your ceramic core placed into the aluminium die, and obviously we inject wax around it. So that's the process of that, really, which is complex in itself. Again, we've not made casting. A wax that's got the soluble core removed, so you can see all the detail on the inside, and show you what the soluble core does in that particular case. Martyn's mentioned about the shelling side of things. For those of you that aren't so familiar with the investment casting process, for this particular part, we have what we call a pre-wet coat, single prime coat. So arguably one of the most important layers, let's say, of the shell is the one that's in contact with the metal. So once you've got a really good fine coat, no bubbles, really good definition, it has to dry properly as well. So we have some techniques to allow the shell to dry, checking temperatures inside the drying as well to make sure all the moisture's been removed, to make sure that first layer is absolutely dry before we apply the next coat. Each part is different. I mean that in the sense that each different type of component is different. So this particular Bentley B here, in this configuration, has one single prime coat. So that's the first coat that touches the metal. And then behind that, we've got some fine coats, and then finally 2 rough coats or backup coats to give the shell the strength. If this was a different component, we'd have a different sequence. We'd always have a single prime coat or maybe a double prime coat, but we might play around with these different coats as well, just to try and get different shell strengths or profiles, depending on if we've got deep pockets, for instance, which might be quite difficult to dry, or if we're having some issues where the shell is getting particularly thin, we might put an extra backup coat on. So over the course of the process and the time that we've been doing this, we found that this sequence works completely the best. So it is a little bit trial and error. This is a picture of a wax assembly that's already had, I think its first fine coat put on in this one here. And this is a picture of the very last coat. So before it goes into the boiler clave to have the wax removed. So this is usually around about 7 to 8 millimeters thickness. Again, Martyn mentioned it in an earlier slide. So literally you've got the shape and then you offset that by 6, 7, 8 millimeters, and then you've got your thickness of shell. So it's only that's separating that 6 millimeters of shell. It's only that's separating the liquid metal from the atmosphere. It's quite amazing. Post-cast operations, is this you or is me?
Well, yeah.
I'll let you do this one.
Okay, so we've produced some castings now, and then we had a series of post-cast operations to go through. I mentioned earlier about part marking for traceability. We put a data matrix on. Again, you'll see on some of these emblems the data matrix that can be read with a scanner. Removal of core leaching. The HIP process, which is done at Bodycoat Chesterfield. That's to close down any micropores within the material. Because it's a mirrored polished stainless steel, without going through the HIP process, it would uncover very small pores, gas-related pores at the surface, which ordinarily you wouldn't see. But obviously by removing that initial 0.1, 0.2 of material, without the HIP process, then there would have been gas pores. Again, process learned really from previous emblems. Machining, there's machining requirement within the wing seating area, and there's an M6 thread at the base of the stem for assembly onto the mechanism. We talked about the smoothness of the internal wire routing channel, and we learnt through prototyping that we needed to include extrude honing process, or an AFM, abrasive flow machining, which initially we were having done by a subcontractor, but we put our own machine in fairly quickly into the series production. And then, of course, final inspection, visual inspection, and 100% gauging on those features. That's it, Russ, on that one. I'll let you go.
Thank you. So traceability was obviously a big thing for Bentley, and the way that this was tackled was to basically have a data matrix, which is a little bit like a simplified QR code, laser etched now into the part. So every single Bentley B and plinth has this unique code, allows for full traceability throughout the process. So not only is this critical for, obviously, from a Lestercast point of view, but the rest of the supply chain use the data matrix as well for traceability. What's on the data matrix? Well, it's a unique number, and this is an example of a unique number on here. So if you were to scan this code, you'd see this sequence of digits. So we've got the first 4 digits are our melt number, which is obviously sequential. The cast date, the sequence ID. So that particular part is number 16,502. So you can see already how many we've done so far. And then the type, so E or P as to emblem or plinth. So on the occasion that we need to then go back retrospectively and try and find when was this particular part cast, we can pull the data from there. We have production cards which obviously record all of the casting data, who manufactured it, when was it made, when did it go through shelling, how many coats did it have, when was it poured, etc., etc. So we use this, and this little square piece here was part of the design that Bentley came up with, maybe in conjunction with Lestercast as well, to try and find an area, obviously, that would allow you to have the data matrix and keep it there, because obviously it needs to stay within the component, but obviously not be visible on the vehicle. So you'll be able to see when you come and have a look at some of these castings here, particularly this one. This one's got a data matrix on it, but obviously it sits below the line here, the plinth, so you obviously can't see it unless you take it apart. So this is all done at Lestercast. So obviously once the parts have been manufactured, they go through this process, and we have a unique laser marker that allows us to put this on, which you can see here. This is a fixture that we designed in-house. Allows us to do 4 parts in a sequence, and we have a scanner here which is linked to a record, so we can zap it and put it onto a record, so that suddenly becomes a live part, if you will, and then we can track it through, and obviously it stays from a traceability point of view. So we have an operator that basically sits here and sets these 4 parts up, goes away, comes back, 10 minutes later, and this is done. So the data matrix is obviously done purposely, so it's quite deep, because obviously it needs to survive quite a few aggressive processes: shot blasting, core leaching, polishing, etc., and obviously needs to stay visible for the entire life cycle of the part. So it's a really good addition, and something that is quite crucial to this part, and the same with the plinth. Core removal, the ceramic core removal. Martyn's mentioned the core leaching. So we've already, in terms of the timeline of manufacturing the component, we've poured the part, we've knocked the part out, we've shot blasted it, we've ingated it, etc. And now we've got to remove the core. The core being the shape that it is, an S shape, it's very difficult to remove by mechanical means. So working with LBBC and Bentley at the time, Leeds and Bradford Boiler Company, who supply us with the boiler clave. I think they're the world leaders in that sense. So most investment casting foundries around the world actually will have an LBBC boiler clave, but they designed this, which is a core leaching machine. Effectively, we put the parts into a basket in a configuration up to 90 parts per cycle, and over the time of around about 4 hours, it goes through a washing process. So potassium hydroxide goes into this vessel here, which is where the parts are located in a basket in a configuration. And basically it gets soaked with potassium hydroxide. It agitates as well through air pressure, and then it has a water rinse and a flush. And that happens multiple times over the space of about 4 hours. In doing so, the potassium hydroxide in this particular percentage attacks the ceramic core. It doesn't damage the casting, which is obviously very important. So that's the best way of removing, or the only way really of practically removing that very small core with that channel through this component. It couldn't be done through mechanical means. You couldn't try and get a little Dremel in there around the corners. It wouldn't be cost effective anyway, and it won't be guaranteed. So this is the best way to do it. And obviously every part goes through this process as well. Operating temperature in here is between 140 and 160 degrees. And I say it does a really good job for us. This is part funded by Bentley. So yeah, it was in their interest to get this put in with their help as well. So yeah, without that, we wouldn't be making the part today. That's for sure. I think over to you, Martyn.
Yeah. Again, don't want to get into too much detail because I can smell the curry. The HIP process is a high temperature under extreme high pressure, and it will push away any small micropores within the material structure. If you get the opportunity to go body coat at Chesterfield, it's quite amazing. Some example parts with large cavities inside the component, and after the process, those cavities are filled. Of course, that material moves from somewhere else. So we were always mindful that if we were going through the HIP process, what it would actually do to the geometry of the part. Thankfully, we get no distortion or movement during that process, and it's not given us any issues on dimensional. The machine inside, a little bit complex in the wing seating area, obviously trying to follow profile. Again, guarantee of geometry, repeatability on the wings themselves. So the parts are located uniquely onto each wing geometry at the back. So if there is any movement there, it will always machine within the profile. There's also some machining on the bottom face, shown there in red, and an M6 thread, and similarly around the wing seating area. The extrude honing process, it's an abrasive media inside a pressure vessel. So this is the machine. Inside here, we have the abrasive media, and the components are fixtured up. And basically, the abrasive paste is pushed up through the cavity and then dragged back through again. So it's a bit like sandpaper in a casting, but it's quite automated. So again, a 4-station fixture for the AFM side of it. And the guarantee and the check that we put in place is if we can pass a cable tie through there, then we know they'll get the 2 wires through there. So every part that leaves Lestercast goes to the polisher with a cable tie up the hole, and that's eventually used by the assembler to then drag the wires back through. So just a simple B&Q cable tie resolve that issue. I've got a video, I think, of the cable tie check. If I just click on that. So you can see now after the extrude honing process, how freely that cable tie passes through that fairly complex geometry and allows the cables then to be pulled back during the assembly process. And we entered the emblem into the CMF Component of the Year award a couple of years ago. We didn't win it, but it attracted quite a bit of interest from Bentley, and they wanted to come on site. They did a press release about Lestercast and about the process, and we've got a short video just to show you of the manufacturing process, so hopefully that will run. There was some sound, but I don't know what's happened, so just sing along to it if you wish. So here you see the core assembly process that Russell's referred to, wax injection process. We form part of the feed technique in the die, so every wax pattern also produces its own feed and feed bar to aid the assembly. We then assemble onto the wax trees. We have a small flame tool for trimming off and putting some wax fillet into sharp corners, all to aid the shelling process. Here you see us going into the prime bath. So this is a zircon slurry-based material. That is in slow motion. So we're looking for full coverage over the wax, allow drain, remove any runs, and then we offer that under zircon sand under a rain cabinet. Once that coat's dried, we then go with the backup material, which is a mullite mineral that's used. Different type of slurry. We are all water-based slurries now. We changed over from alcohol-based materials in 2018. So we are all water-based. And after each coat, they go into a controlled atmosphere, humidity controlled, temperature controlled, with a lot of wind movement. And that's just Russell. After de-wax, we then preheat in a preheat furnace, heating up to 1,000 degrees for the shell. And once the mold is ready, it's acting as removes any residual wax that's in there. It's also firing the shell, and it's preheating, ready for casting. So we're casting at around about 1580 degrees C. Mold is offered onto the furnace, as Russell described earlier. The furnace rolled over, contents of the furnace deposit into the shell, and then the shell is put aside for cooling. So you can see there what we've replicated in simulation is what we've got in real time. Mold is put aside till it's cool enough, then we can remove the shell. That was just for the video. We don't use a hammer in production. It's a pneumatic in a cabinet. And then we've got to remove the ingates, the feed gates. We leave a small amount of profile there so that we don't damage. The machinist takes a bit more away, and then the polisher takes the remaining bit that's left. After core leaching, we do a quick pressure test there to make sure we've got a cavity. That was an old percussion marker that we used to have before we put the laser marker in. And of course, we've got some fairly standard CMM programs that check various aspects of the finished part. Reading the data code. And now this bit is actually at the company that does the assembly. Bentley wanted to include this in the video, so there's just a couple of minutes of how the cable are passed through, PCB board in position. The lenses themselves are acrylic and are glued using a UV system. There was some suggestion of lead crystal ones, but I think it pushed the cost down. So it's plastic. But the effectiveness is good in terms of illumination. There was a lot of rendering done on software to get the illumination. And that's where some of the detail on the inside of the wings dictated as going for a soluble core. There's some fluting and detail on that. You'll see that on the core. And that was for the illumination. And then there's the assembly into the actual mechanism itself, which you saw on the previous video. This is the knockdown test. So again, on impact, it's got to drop into the bonnet. In 2 directions. And then you see it going into vehicle assembly. And the small control box that we've got on our demo equipment there is the equivalent of what the driver has in the vehicle. And you can also do it off an app, off your phone as well. So if you park your car and you forgot to put your emblem down, you can do it while you're sat having your champagne later at night. So very quickly, the supply chain. So we are tier 3. We were originally asked to take tier 1, which would have meant responsibility for polishing. We didn't really want that. It's not our expertise. So we take tier 3. We then ship the parts to Germany to a company called Scala Design, who hand polish, literally every part hand polished. It also includes a hydrofluoric acid cleaning process, which removes any impurities from that cast surface. There's an electropolishing requirement for the illumination. So the whole of the part is electropolished so that we can get the EP onto the inside of the wings. It's then mirror polished, and then they're 100% corrosion tested because the customer doesn't want to see the emblem going rusty. And these cars go to some extreme conditions, hot and sandy conditions in America in particular. And then after polishing, they return back into the UK to WCM at Basildon, who do the assembly mechanism. And then it's dispatched up to Bentley Motors at Crewe for vehicle assembly. So from start to production 2019, we've produced over 17,000 emblems. It's quite astonishing, the numbers, when average price of this car is £330,000. You know, it makes you wonder where they all go, and at times we couldn't make enough. We're currently at, well, vehicle assembly currently is 85 a week, with 80 of those being mirror polished and 5 being black pack. I won't ask for a show of hands. Hopefully you found that interesting and informative, but if there's any questions, by all means, we'll try and answer. Thank you.
Thank you very much. I think we'll all agree that was an excellent insight to something incredibly complicated, and well done, Lestercast. You know, brilliant. Any questions? One at the back. Oh, we'll go to the side first.
Do you only cast in steel, stainless steel?
No, we do high temperature alloys, so duplexes, nickel, Inconels, Astalloy X, high temperature application. We do aluminium, A357, LN25, LN4. We do brass, we do bronze. If it's castable, we'll have a go. As I said, we just don't do any iron at all. And it's strange, the investment cast process doesn't seem to attract irons for whatever reason. I think there is probably one company I've seen that does iron in investment process, but it tends to be the steels and aluminiums.
Question at the back. Just testing my ability to pinch a chip on route. Look.
When you build up a mould, you're using different materials. Are they easy to recycle afterwards, or do you have to scrap it all off?
Well, all wax is recycled. So the wax, which is the hot tree, and the patterns themselves, goes through the autoclave, which is the high steam pressure vessel for removing the wax. That is using the exhaust pressure from the machine. It pushes a slug of wax basically outside to a collection vessel, and that wax then goes back to Blasons and is refined and reused again wherever in the world as investment wax pattern material. So the waxes are recycled. The ceramic just breaks down in the caustic solution. The soluble is dissolved in the citric acid, and the only thing that goes to landfill is ceramic. At the moment, we have been doing some work with the CMF over the last few years about what we could do to recycle the ceramic, but at the moment it goes to landfill as a product. But if we could find a solution for processing that shell, that would be the only thing really that's left that's not recycled.
Any more questions? Any questions online? No. Okay, I'd like to call on Darren to provide the vote of thanks.
Thanks, Trevor. That's an absolutely fascinating presentation from start to finish. You really have set the bar very high. Seeing the layers that you've gone into and the challenges that you've had off Bentley and the passion that you've shown, seeing the project through from start to finish is incredible. I think everybody in the room looking around periodically, everybody's been absolutely captivated with your presentation, and we can't thank you enough. Lestercast for your generosity, and Martyn and Russell, thank you so much. If I can ask the room to join with a round of applause in the usual way to say thank you.
We was only expecting one presenter tonight. No, we'll make sure that we get another one too. But if you'd like to step forward.